Hey guys, I just want to take a few minutes and do a video specifically on the fine-tuning effort that I was involved in finding an optimal back focus for the field flattener that I have for the ED102. This is a continuation of the last video. I decided to take this part out just because it made the previous video too long to contain this particular topic in it as well. Basically, this is a problem that I've had and I've known I've had for a while, which is to say I've got some stretched stars in the outer perimeter of the images I'm taking with the ED102. I bought a field flattener, and the theoretical back focus spacer I need to get the 55 millimeters of back focus required for the field flattener is a 12 millimeter spacer. I've been using an 11.55 millimeter spacer, which seemed like that should be good enough. It wasn't. And I did a series of tests with the 11.55 millimeter spacer and some shims. That didn't work, so I bought a shorter spacer, a 10 millimeter spacer, and repeated those tests. And let's go over to the telescope and I'll show you what I'm talking about. Okay, so here we are at the refractor, and this is just to kind of set things up for the spacer study that I did with everything hooked up. We have the click lock, we have the shoulder of the flat fielder, requires 55 millimeter of back focus from the forward edge of the off-axis guider back to the sensor in the camera. Now the question is, what is that 55 millimeters? Well, if you add up all the parts, and just take a strictly part count and part width and add that up, you have 16.5 millimeters for the off-axis guider, you have 20 millimeters for the filter wheel, you have 6.5 millimeters for the setback of the sensor within the camera, which leaves 12 millimeters as the nominal spacer dimension. And that's a good starting spot, and that's why I've been using this 11.55 millimeter spacer that came with the Celestron off-axis guider. However, with that even, I found that I had stretched stars, so clearly that wasn't good enough. And now the question is, what is the actual space requirement? Well, good thing that ZWO provides some spacer shims, as we see here. I must have gotten a set of 3 with the filter wheel and another set of 3 with the camera. And basically you have a fairly thick one that I've measured out to be about 0.5 millimeters thick, and then you get 2 fairly thin ones that I measure out to be about 0.15 millimeters. So you get 2 sets of that, and then you can combine these in various combinations with spacers to put in that interface to find, hopefully, the optimal setback so that you get the exact 55 millimeters and a flat field. Now, there are other options. ZWO provides an adapter, this thing here, which comes as 2 pieces, an 11 millimeter adapter here, and then a thread changer here, so you can screw it into the back of the filter wheel. Now, those 2 things together add up to 13. So I did a series of image tests, where I had the 11.55 plus some combination of these shims and put those in and ran through a series of tests, taking pictures at night, looking at the stars in the corners, and I couldn't find any combination that gave me a flat field. The spacers that I have are too large, so I went out and bought a 10 millimeter spacer. You can't barely see it in here, but it's between the off-axis guider and the filter wheel, so it's 10 millimeters, and I repeated this test the other night and came to the conclusion that the 10 millimeter spacer plus one of these flimsy 0.15 millimeter spacers gives me the best, not perfect, but the most flat field that I can seem to get with this setup. Let's go into PixInsight and take a look at the results from those tests. Okay, here's a side-by-side comparison of the upper right-hand corner of the images that I had when I used the 11.55 millimeter spacer. And remember, 12 millimeter spacer is the theoretical width of the spacer to get to a 55 millimeter back focus without any other considerations, just the thickness of parts. So this is an 11.55 millimeter spacer over here on the left, and you'll notice that I've got some stretched stars in the upper right-hand corner. I've got stretched stars in the lower right-hand corner, and stretched stars in the lower left-hand corner, and stretched stars in the upper left-hand corner. Now, what I did is went through a series of tests where I would take pictures like this using different combinations of the 10 millimeter spacer and the various shims that I have from the ZWO shim sets, and came up with this particular combination, which is the 10 millimeter spacer and the 0.15, one of those thin, very thin shims that the ZWO provides. And so this is what I found. It's not going to be perfect. It's not perfect, but it's certainly better than what we're seeing over here with the 11.55 millimeter spacer. So in the upper right-hand corner, I'm getting pretty decent round stars. Down in the lower right-hand corner, however, I've still got some image defects. It's not a uniformly stretched star, but it's arguably better than what I had before. In the lower left-hand corner, the stars are not too bad. There's still a little bit of defect going on cosmetically in the stars, but still it's better than what I had. And then going up to the upper left-hand corner, it's decent. Okay, so I'm getting, I don't know how much perfection to expect from the field flattener, but at least this combination of a 10 millimeter spacer and the 0.15 millimeter shim is seeming to do a decent job with giving me round stars around the periphery of the image. Now, of course, now that I've changed the spacing between the off-axis guider and the camera, I also have to refocus the guide camera, which is now the ASI 290 Mini. And let me show you what I got from that. But first, let me show you, this is an image where I did some focusing outside with the ASI 290. This was a different filter set or a different spacer set combination. I had a 10 millimeter spacer and a 0.2 of the 0.15 millimeter shims. And so this was not quite the optimum spacing that I ultimately found, but you kind of get a sense of what the guide stars would look like with that combination. And it turned out to be fairly easy to focus just by looking at the light, looking at a star, and then just barely raising or lowering the camera within the holder and then tightening the set screw to lock it in place. So this actually turned out pretty well, but I think it's useful to take a close look at what we're seeing here. Now on the right hand side, this is the part of the image that's closest to the center of the light cone of the light coming down the telescope. It's still offset from the center, but it's the part closest of the sensor, closest to the center of the light cone. And then as you go out to the left here, you're going farther out into the away from the center of the optical center. So let's zoom in a little bit here and look at the stars are not perfect. I get kind of almost like an arrow type shape to it, so it's not perfectly circular out there. But again, this isn't the optimum combination of spacers either. The interesting thing happens on the other end, because as we go farther and farther out, we can see that we are getting more and more stretched stars. And for example, this guy here, if you selected this for a guide star, it's not going to be a perfect circle, and so the algorithm used to compute the centroid of this star may or may not be consistent over time. The bigger effect, though, would be taking the light of a guide star and stretching it over several pixels. So in effect, you are losing signal-to-noise ratio in your guide stars when you have stretched stars. So that's another important reason to try to get a flat field other than just the cosmetic effect on your images. If you're using an off-axis guider, you're going to take a little bit of a performance hit probably with having stretched stars. Now, let's go down and look at the focusing. What I do for focusing, as I mentioned in an earlier video, is use my imaging train with the Red Cat 51 and then focus on the fence, which has a lot of nice wood grain and lines for using edge detection algorithms for improving focus. So this is the imaging camera, and I use SharpCap and the edge detection focusing aid that's in SharpCap to gain focus for the imaging camera. And then I repeated that with the guide camera, and this is what I got. Okay, so over here, if we go back to a 1-to-1 scale, you can see that we're doing pretty good. Let me brighten that up a little bit. You can see that we're doing pretty good. It seems to be fairly well in focus. Likewise over here, if I go to 1-to-1 scale, you can see that we're very nice crisp line. So I think this is a pretty good way to focus. The interesting thing about this is if we go back out, you can see we have a shadow zone over here. Let's increase the light, and you can see we can dig back in and still see some wood grain back here, but mostly what we're ultimately going to find is that there is this curved edge here. That curved edge is the aperture, the hole through the central column of the off-axis guider that light is reflected through. So light comes down the axis of the telescope, it reflects off the 45-degree mirror, and then it goes straight up through a circular hole until the light hits this sensor. And so what you're seeing here is that with this ASI 290 sensor, which is fairly long compared to its width, I'm using most of the sensor, but there is this edge here where we're seeing the curved boundary of the hole through the pillar that contains the prism in the off-axis guider. So this is the edge of that hole, and we're not able to really make effective use of the sensor at least about 1/8 of it, of its length out here. And that's just something to keep in mind. But it's also a reason why you don't want to waste money on a sensor or a camera with a large sensor and pair that with an off-axis guider that only has a small prism, because you'll never be able to make use of the whole sensor. In this case, I can make use of the full width of this sensor, but not quite the full length. Okay, so let's turn our attention back to the spacers for a minute. Why is it that a 10.15 millimeter spacer seems to provide the best image when our calculations would suggest that we need a 12 millimeter spacer? And I think we can get some insight into this if we go over and take a look at the CAD drawing. Here's the click lock. This blue piece is the field flattener. Then we get into the off-axis guider with the ASI 290. We have the spacer, which again theoretically should be 12 millimeters, but we're finding that 10.15 works better. We have the filter wheel, and I've drawn the filter in here, and then of course we have the camera and the setback of the sensor from the face of the camera. So the interesting part here is down here in this zone here. Let's zoom into that area. So what I'm showing here is light coming in from the objective. It comes in through. Now if there were no filter here, the light would come straight on through, and we would be able to focus back on the face of the sensor here. And this is where the light would be focused. But what's actually happening is as the light enters this denser glass, the speed of light is slower, so we get a refraction effect and it bends the light. And then as the light emerges from this denser medium, it then goes parallel to where the light was. But what happens is the focus point now shifts from here back to here because we put that glass between the sensor and where the light entered. And so we're actually, if we're going to calculate a spacer dimension, we've got to subtract off this amount. I've got to reduce my spacer length by this distance. Now this is an exaggerated drawing here, but there are articles out there that you can find where the optimum or recommended correction is the thickness of the filter glass divided by 3. Now for a ZWO filter, they're about 2 millimeters thick, so 1/3 of that is 0.67 millimeters. That's not a trivial amount given what we're trying to achieve here. So I have to take the 12 millimeter spacer and subtract 0.67 from it to get the ideal spacer. But that's still longer than what I ultimately ended up with. Now what I found is when I took the calipers and measured from the forward face of the off-axis guider to the back face of the filter wheel, I measured 47.4 millimeters. All right, let's go and look at some of the calculations on that. So I measured 47.4 millimeters. What would we expect it to be based on manufacturer provided dimensions? Well, we have the 16.5 millimeters for the off-axis guider. We have 10 millimeters for the spacer. We have 0.15 millimeters for the shim, and then we have 20 millimeters for the filter wheel. Now that adds up to 46.65, but I measured 47.4 millimeters. So where's that extra length coming from? Well, it comes from interfaces. Just because you put two pieces together, it doesn't mean you have perfectly flat faces bearing up against each other. In fact, there'll be some residual gap that builds up that is present at each interface, and essentially that's what we're seeing. So the difference between the 46.65 that we theoretically expect and the measured 47.4 that I actually measure is some of that lost width in the gap in the interfaces between the parts that are being connected together. Now, let's take the actual measured 47.4. Let's add on the filter effect, the refraction effect for the filter. So that's 2 millimeters divided by 3, plus the sensor setback from the face of the camera, and we come up with 54.5, which is pretty darn close to 55 millimeters. So even though you go through this calculation, if you ignore the filter, you expect that you need a 12 millimeter spacer. What you find in reality is that 10.15 works best from an imaging perspective, just taking pictures, looking at the images. And then when you go through and actually make some measurements and account for the filter and the gap, the interface thickness, if you will, for the various pieces being put together, you come up with a number that's pretty close to what we're looking for, which is 55 millimeters. So I think we're on the right track with this particular combination of 10 millimeters plus the 0.15 millimeter shim, and that's giving me a pretty decent back focus for the field flattener. So let's just go through those findings from this little study, side study I had during my imaging session. First of all, the stretch stars in the corners of the images are cosmetic effects that we'd all love to get rid of. I certainly would. But if you're using an off-axis guider, there's that secondary effect that you're using stretch stars to guide with, and that may create additional problems. What I've found is that manufacturer-provided dimensions for the thicknesses and optical lengths are a good start, but direct measurement is better, so I'd recommend anybody doing in this hobby to get a pair of calipers and make your own measurements. You need to account for refraction effect through the filter glass. That's not an insignificant amount. Filters can vary depending on the manufacturer, 2 to 3 millimeters, say, and that can be a pretty significant offset. So take the thickness of the filter glass, divide it by 3, and you need to subtract that from the theoretical spacer width that you would normally pick in order to pull that focus point back to the face of the sensor. Just keep that image from that CAD drawing in mind when you're thinking of that. I would recommend doing a series of imaging tests with spacers and shims. It's a pain in the neck because you have to configure your optical train one way with a spacer, take a picture, pull the image, look at the image in the corners, take the system out, replace the spacers with some spacer and shim combination, take another picture, and repeat that process with a number of different combinations, and then go through the final results to see which combination provided the best image. Like I say, it's a bit of a pain, but it is probably the best way to confirm what you're looking for. I still got some image defects. Now there's some other things going on that won't be solved with back focus. A secondary effect, maybe not important for stretch stars, is getting a good focus. One of the things I mentioned in the previous video is that I'm not doing as good a job as I should. I need to start using the one-to-one display mode, that is where the imaging camera pixels are equal to a computer pixel, so it's one-to-one, with numerical focusing aids such as the Bahtinov grabber or full width at half maximum. Those numbers are using your laptops or your computer's pixels to make judgments about your optical system performance or focus, whereas the ideal thing is to use the imaging camera pixels, and the one-to-one display mode achieves that. So that takes the pixels of the imaging camera and makes them equal to the pixels of the numerical focusing aids you're using. I will certainly have some residual error due to camera tilt. This whole imaging train slips into the click lock, which you then turn or rotate, and it grabs it and holds it tight with friction. But there's probably going to be some residual tilt in that system. It's not a fully threaded connection, so I'm going to have more tilt than somebody would who had a fully threaded connection all the way back to the imaging sensor. That's just a price of doing business, I suppose, with my setup. and so I will have some tilt. Now, there's another effect. The click lock is a nice solid connection, in part because it squeezes pretty hard on the barrel of that field flattener. The downside to that is that as it's gripping the barrel of that field flattener, it's also applying compression and otherwise slightly, ever so slightly, deforming the optical element. And to some degree, that compression, that stress and strain that the optical element is under may be contributing to some of those image defects that I have. I don't know about that. I'll have to do some additional tests maybe and see if applying less compression improves the image quality at all. But at this stage, I just need some good weather and get outside and try taking some more images with this improved back focus arrangement. Okay, I just wanted to share these ideas with you. I'll talk to you guys later. See ya.